Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Joule-Thompson effect for a perfect gas and Van der Waals gas with the concept of temperature inversion. Let's begin. We know from Joule-Thompson effect, or we can say it as Joule-Kelvin effect, the Joule-Kelvin coefficient, we know Joule-Kelvin coefficient is expressed as that is dT by dP, change in temperature with respect to pressure, is equal to 1 by Cp T del V del T at constant pressure minus V. That is the thermodynamic expression or thermodynamic explanation of Joule-Thompson effect. We get that relation, that is Joule-Kelvin coefficient, change in temperature with respect to pressure. With the help of that particular expression, we can easily find out the Joule-Thompson effect for perfect gas and Van der Waals gas. First one, for perfect gas, what happened? Perfect gas, or we can say that is the ideal gas. Ideal gas. The perfect gas equation, if we take 1 mole of perfect gas, if we take 1 mole of an ideal gas, then the gas equation is PV is equal to RT. N is equal to 1 here. The volume V is equal to RT by P. Now differentiating with respect to temperature, taking as pressure as constant, then what happened? Now differentiating with respect to temperature T at constant pressure P, we get is del V by del T at constant pressure is equal to, that equation is written as R by P. Differentiating with respect to T, this is the value of del V by del T at constant pressure. Now we can substitute that throughout the Joule-Kelvin coefficient expression. So now substituting the value of del V by del T at constant pressure in the expression of Joule-Kelvin effect or Joule-Thompson effect. Joule-Thompson effect, that is dT by dP. So dT by dP is equal to 1 by Cp T del V by del T at constant pressure minus V. Here we take 1 by Cp, that is T, in place of del V by del T at constant pressure, that is R by P, that is R by P minus B. So here T RT by P is equal to PV, as we show here PV is equal to RT. So in place of RT by P, that is V, is equal to 1 by Cp V minus V. The quantity will be 0, means dt by dp is equal to 0. Hence Joule-Thompson coefficient is 0 for a perfect gas. Joule-Thompson coefficient is 0 for a perfect gas. Now we have to calculate Joule-Thompson effect for a Van der Waals gas. This is for perfect gas. Now for Van der Waals gas, second one, for Van der Waals gas, if we take 1 mole of a real gas, or we can say Van der Waals gas, then gas equation will be, gas equation is given by P plus A by V square V minus B is equal to RT, where A and B are Van der Waals constant. Van der Waals constants. We can express that equation as PV minus PB plus A by V minus AB divided by V square is equal to RT. Here the term AB by V square is neglected, as we take A and B are the Van der Waals constants, are very small quantities as comparison to that of quantity V square. V square is the volume, so that term is neglected. Here AB by V square is neglected. So we get, why neglected? Since A and B are very small as comparison to the volume. So PV minus PB plus A by V is equal to RT. Here we get PV is equal to RT plus PB minus A by V. As we know, PV is equal to RT, so V is equal to RT by P. So instead of V, we write that is RT by P. Here we get PV is equal to RT plus PB minus FP by RT. Now PV is equal to RT plus P taking as common, that is B minus A divided by RT. Now differentiating that equation with respect to the temperature term, keeping pressure as constant. So what we observe, now differentiating, right here, differentiating the above equation with respect to temperature T, keeping pressure as constant, we get P del V by del T, or constant pressure, is equal to R plus Fp divided by R. Here we expand it in two terms. One term PV is constant, so that differentiation will be 0, only that term. differentiation factor is equal to 1 by T square. Is equal to del V by del T at constant pressure, that is R by P plus A by R into 1 by T square, that P is divided. So, del V by del T at constant pressure is equal to R by P plus A by RT square. Now, we can substitute the value of del V by del T at constant pressure in the expression as Joule-Kelvin coefficient expression. Joule-Kelvin coefficient expression, we get the result. So, here substituting this value of del V by del T at constant pressure in the expression for Joule-Thompson effect. Joule-Thompson effect, that is dt by dp is equal to 1 by Cp T del V by del T at constant pressure minus B. So, in place of del V by del T at constant pressure, we put that value here. So, we have 1 by Cp T, that is R by P plus A by RT square minus B is equal to 1 by Cp RT by P plus A by RT, 1 T cancel out, minus B is equal to 1 by Cp RT by P, that is V, sorry, here we take RT by P as V, as we write here RT by P is equal to V minus B whole into B minus A by RT from Van der Waals gas equation. From Van der Waals gas equation, look here, this is the Van der Waals gas equation. We can get the value of RT by P from this Van der Waals gas equation. The RT by P value is find out. Here we put that value in place of RT by P, that is V minus B minus A by RT plus A by RT minus B is equal to 1 by Cp minus B plus A by RT plus A by RT plus A by RT, right, 2A by RT, that is 1 by Cp 2A by RT minus B. Therefore, dt by dp is equal to 1 by Cp 2A by RT minus B. That is the Joule-Thompson expression for real gas or Van der Waals gas. Since it is for Van der Waals gas or real gas, then there are 3 possible cases we have to find out, as the term 2A by RT is here, 2A by RT minus B term is here. There are three possible cases. Maybe that term is positive, maybe that term is negative, maybe that term is 0. Then what are the possible scenarios in each special cases? So, special cases, first one, when 2a by RT minus B is positive, then what happened? The term is positive means that is 2a by RT minus B is greater than 0. So, 2a by RT is greater than B, or T is less than 2a by RT. Then the term del T by del P, since T is less than 2a by RT, so del T by del P is the positive quantity. Then del T by del P is positive quantity. Since del P is always negative, so positive value of del T by del P implies that the term del T should be negative. Since that term is positive, that is negative, so that term obviously be negative. In other words, we can say the cooling effect is observed. The cooling effect is observed when the temperature is less than the quantity 2a by RT. So, 2a by RB here, not RT, that is 2a by RB, 2a by RB. Okay. So, the cooling effect is observed here, at that particular condition. Now, case number 2, if the term is negative. Case number 2, if the term is negative. Case number 2, when 2a by RT minus B is negative. Negative means that quantity is less than 0. That is why 2a by RT is less than B, or RT by 2a is greater than 1 by B, or T is greater than 2a by RB. Then the quantity del T by del P is a negative quantity. Then what happened here? Since del P is always negative, so del T will be positive quantity. In other words, we can say here In other words, heating effect is observed. Heating effect is observed when temperature is greater than 2A by B. Heating effect is observed here when 2A divided by RT minus B is negative. Next, third possible scenario, if that quantity is equal to 0. Third special case, when 2A by RT minus B is equal to 0. That is 2A by RT is equal to B, or T is equal to 2A by RT. Then del T by del P is equal to 0. Thus, del T is equal to 0. Change in temperature is 0. So, we can say it implies that the gas on passing through that of porous plug, the gas passing through that porous plug shows no change in temperature, no change in temperature. Here change in temperature will be 0 temperature when that T is equal to 2A by RT. This temperature is called temperature of inversion. This temperature is called temperature of inversion. Temperature of inversion, the temperature at which heating effect changes to cooling effect. Temperature of inversion, and mathematically we can write it. Mathematically we can write it, the temperature inversion, temperature of inversion Ti is equal to 2A divided by RB. At that particular temperature there will be no such change in temperature. The temperature is known as the temperature of inversion, and according to the temperature of inversion, the Joule-Thompson expansion can be treated as, the points we have to remember here, if T is less than Ti, then that indicates cooling effect. Cooling effect. And when, if here T be the initial temperature, here T, that is the initial temperature, and Ti is the temperature of inversion, that is initial temperature is less than Ti, then cooling effect. Then if initial temperature is greater than that of temperature of inversion, then we observe heating effect. Heating effect is observed, and if the initial temperature is equal to that of temperature of inversion, then we observe no change in temperature. No change in temperature is observed here. So, here we get cooling effect, heating effect, then no change in temperature. Now, if we plot a graph by taking the pressure difference, if we plot the graph by taking the pressure difference dP in y axis and temperature on x axis, as we know, the enthalpy H is equal to U plus PV. Enthalpy H is equal to enthalpy H is equal to U plus PV. U is the internal energy, pressure into volume. That enthalpy is always constant at all points throughout the curve. If we plot in that of graph, all points enthalpy is constant. And the curve obtained in that graph is called the constant enthalpy curve or isoenthalpy curve. That curve is known as constant enthalpy curve, constant enthalpy curve or isoenthalpy curve, isoenthalpy curve, constant enthalpy curve or isoenthalpy curve. As we take enthalpy as constant, then the curve is obtained. At the highest point P, highest point B on that curve, here dt by dp at that of highest point B here dp by dt, dt by dp change in temperature with pressure will be 0 here, or we can say that is T is equal to Ti, or T is equal to Ti here at the highest point, where Ti is the temperature of inversion and T is the initial temperature. For the temperature less than that point, less than let OA, that region, the cooling effect is observed. Here dt by dp is less than, that is greater than 0, or we can say temperature is less than Tc, and here the cooling effect is observed. The effect is known as cooling effect. Again, at this portion, heating effect is observed. Here dt by dp is less than 0, or initial temperature is greater than temperature of inversion, and that process is known as heating effect. Here we observe heating effect of that portion. Okay. Throughout that particular graph, we can easily conclude how cooling effect, heating effect and no change in temperature is observed. So, with the help of this video lecture, we understand the Joule-Thompson effect for a perfect gas and Van der Waals gas. We take the referent equation as Joule-Kelvin coefficient expression. By using that, we calculate Joule-Thompson effect for a perfect gas or ideal gas. Here that will be 0, and for Van der Waals gas or real gas, this is the expression or Joule-Thompson effects for Van der Waals gas or real gas. There will be 3 possible cases by taking that term 2a by RT minus B. So, if that term is positive, then we observe the cooling effect, and if that term is negative, then we observe the heating effect, and if that term is 0, that is no effect is found, that is known as the temperature of inversion, and at the temperature of inversion, by taking as reference point, we take how the cooling effect, heating effect and no change in temperature occurred. Now, with the help of that isoenthalpy curve or constant enthalpy curve, we can easily show how all these heating phenomena, means cooling effect, heating effect and no change in temperature occurred in that of particular graph we conclude. So, with this useful and informative notes, let me wind up this session. Thank you.